sac437 problem number 1. Supposed to determine the free electron density. That is the charge carrier density for copper. And we're supposed to start by looking up the atomic mass of copper. I'll use the symbol M. And on the periodic table in the back of your textbook, it's given as 63.546. We can take that as atomic mass units per particle, atomic mass units per atom, for instance, or it also represents the number of grams per that 1 mole of the substance. Has. Represents the mass of 1 mole of the substance. 1 mole of copper has a mass of 63.546 grams, so I'll write it as 63.546 grams per mole. And then in part B, we're supposed to get N mass, the number of particles per unit mass, per gram or per kilogram. I'll say N mass. Well, just looking at the units, it's going to be, if it was the number of moles per gram, it would be 1 over 63.546 grams per mole, or 1 mole. Where a mole is just a certain number of particles, Avogadro's numbers of particle per gram, so I'll just multiply that by the number of particles per mole, which is Na, Avogadro's number. I could, in terms of a formula, say that this N mass is equal to 1 over MCU times NA, which is then equal to what I've written here, where NA is 6.022 times 10 to the 23rd particles per mole. In this case, the particles are atoms of copper. And multiplying that out, I find the number of particles per unit mass. Yeah, let's get that into units of kilograms. I'll multiply that by 1,000 grams per kilogram and get the answer in SI units. So N mass in SI units turns out to be 9.48 times 10 to the 24th. Atoms per mole. Per kilogram. Okay, that's the number of atoms per kilogram in mass. And I better look at what they want for C. Look up the density of copper. I found that in volume 1 of your textbook, the Giancoli textbook. This is the one we're using the year I'm writing this solution out. And I just looked up density in the index. It directed me to a page, and there was a table of densities, including the density of copper, which was listed as 8.9 times 10 to the 3rd kilograms per meter cube. And we're taking a step-by-step through this problem of finding the number of charge carriers per unit volume. Calculate N sub vol, the number of atoms per volume. Well, again, by dimensional analysis, like looking how the units work out, the number per volume, number of electrons per volume, and I guess I call that atom density with respect to volume, is going to be the number of atoms per kilogram times the number of kilograms per volume. So it'll be N mass times rho, which is, we found N sub mass to be N 9.48 times 10 to the 24th atoms per kilogram, and then multiply that by the 8.9 times 10 to the third kilograms per meter cubed that we found for the density. And I get number of atoms per volume this is 8.4 times 10 to the 28th atoms per meter cubed. And then we're up to the last part. Part E says, assuming there is one free electron, and that should be written as 1, emphasizing the fact that it's only good to one significant digit, one free electron for each copper atom, and that it's associated with that copper atom. Find out what N is, where N is the number of charge carriers per unit volume, or the number of free electrons per unit volume. So what we've got is, I'm going to write it down this way. N is N sub volume, number of atoms per meter cube, times, I just write it out as number of electrons or free electrons per atom, which is the 8.4 times 10 to the 28th atoms per meter cubed times 1 free electron per atom. You should recognize this is an estimate, this 1. That's why the problems for this Hall effect are just good to one significant digit. In general, you measure everything else in the case of the Hall effect in order to determine the charge density, the conduction electron density, or the free electron density, the number of charge carriers per unit volume. So here, this is an estimate, and it is experimentally found that it's in the ballpark of 1. Call it 1 to 2. We've been asked to assume that for the case of copper that it's 1. And so we get N is equal to 8 times 10 to the 28th charge carriers, I'll say free electrons, per meter cube. Again, value that we consider to be good to one significant digit. Case of copper, this number to 2 sig figs is probably about 1.3, but it depends. Typical copper that you actually find a wire made out of is not pure copper, and hence it depends on exactly what the percentage of impurities are, what alloy you're dealing with that you're calling copper in an actual physical copper wire, which in general is not really pure copper, but it's mostly copper. So we find 8 times 10 to the 28 free electrons